This question is given in GATE 2008 in the subject digital. Okay, now see this question. In the following circuit, the comparator output is logic 1 if V1 greater than V2 and is logic 0 otherwise. The D to A conversion is done as per relation VDAC is equals to sigma n equal to 0 to 3 2 power n minus 2 into Bn volts, where B3, B2, B1, B0 are the bits for the counter outputs. Okay, the counter starts from a clear state. Here clear state means you must know that its state is from 0 0 0 0. Okay, clear state is nothing but it is starting from all zeros. They asked the question that the stable reading of this LED display is option A 6, option B 7, option C 12 and option D 13. Now here is the circuit diagram given. This circuit diagram consists of many things, like many components involved this circuit. Okay, first thing is 4-bit up counter. Okay, it consists of 4-bit up counter B3, B2, B1 and B0. These are the 4 bits for this counter. Now it is connected to a 4-bit D2A converter. Okay, it is converting the digital to analog output, where this output VDAC is converted to this comparator. It is called comparator. It just compares two signals and it will send either 1 or 0 to this output, and this VDAC is connected to the inverting terminal of the comparator, and the other end of this non-inverting terminal is connected with the Vin of 6.2 volts, and this is connected as one of the input to this AND gate. This is AND gate. The other input of the AND gate is connected to the clock, where the output of AND gate is again connected to the counter, as well as this counter gives two things. One is for D to A, other is for binary to BCD converter. Finally, this binary to BCD converter is connected to the 2-digit LED display. This is what the given circuit is. So it simply, from the AND gate, signal is passed through this 4-bit counter. It is sent to the DTA converter. This DTA converter is connected to comparator. On the other hand, this from this counter, the output is taken to BCD, binary to BCD. From this binary to BCD, finally we are getting display here. What they are asking is the stable display. What is the stable display displayed by this? Okay, we need to tell the answer, like what is the display in this LED. Given VDAC equation, VDAC is equals to sigma n equal to 0 to 3 2 power n minus 2 into Bn volts. Okay, now if you expand this, this will be 4B3 plus 3B2 plus B1 plus B0 by 2. This will be 2. Okay, why? Because it is in the power of 2 power n minus 2. Okay, so 4B3 plus 2B2 plus B1 plus B0 by 2. Okay, now this will be the equation for VDAC. Now in this we have two cases here. Okay, so let's see that case 1 will be VDAC less than Vin. In this case, if you see here, VDAC is less than Vin, means voltage at inverting terminal is less than non-inverting terminal. Then comparator will be 1. The output of comparator will be 1. So clock is applied such that if both are 1 for this AND gate act as enable. Okay, AND gate act as enable. So you are getting this point, right? You see here VDAC is one input for the comparator, Vin is another input for the comparator. If VDAC is less than this, means voltage at inverting terminal is less than non-inverting terminal, comparator the output will be 1. Okay, comparator output will be 1. So clock is applied here. For whenever clock applied, I am indicating with 1. So for this AND gate, both are 1. For the AND gate, if we give 2 inputs 1, then the output of the AND gate will also be 1, right? So AND gate act as enable here. Coming to the second case, case 2. In the second case, it is if VDAC greater than Vin. If VDAC is greater than Vin, what will happen? Comparator output will be 0. Comparator output will be 0. So in this case, clock is not applied. Clock is not applied. Okay. Now, if any one of the input for this AND gate is 0, it will be like AND gate will be disabled, or the output of the AND gate is 0. Here enable in the sense the output of the AND gate is 1. So AND gate will be 0. No signal is given to this counter. Okay. Whenever this up counter is stable, clock will not be incremented. Okay. Now we will see these cases with respect to this equation. Okay. In the first case, it will be clear state. The counter will be clear state. We will see VDAC. This indicated by B3, B0, B1, B2 and B3. Okay. Now, just a second. We will write this as according to MSB to LSB. This will be B3, B2, B1 and B0. Okay, this is MSB. Now we will see this. First, clock, whenever this input we are giving, comparator will be enabled. Okay, so clock will be applied. AND gate is 1. So it will input is given to the counter. Counter will be up counter. You see here up counter. So counter will be plus. Counter will be plus because it is an up counter. The output of this counter is connected to VDAC, and the VDAC will be having if you give 0, 0, 0, 1, VDAC will be, this is VDAC. If you write, it will be, you substitute these terms in this equation. Where is it? This equation. If you substitute this 0, 0, 0, 1 in this equation, you will get 4 into 0 plus 2 into 0 plus 0 plus half. So VDAC will be 0.5. Now for the second thing, counter will be incremented 0, 0, 1, 0. This will be here 4 into 0 plus 2 into 0 plus 1 plus 0. So it will be 1. So likewise, VDAC keeps on incrementing, whereas Vin will be constant. This will be obviously less than Vin is 6.2 volts, less than 6.2 volts, less than 6.2 volts, until it reaches a point where 1100. You check this 1100. This will be 1. So 4 into 1 plus 2 into 1 plus 0 plus 0. So this will be 6. 6 is also less than 6.2, right? Yes. Next, it will be incremented 1101. So you check this. You substitute 1101 here. This will be 4 into 1 plus 2 into 1 plus 0 plus 1 by 2. It will be 6.5. 6.5 less than 6.2. Is it right? No. At this point, counter will be stable, because at this point DTA converter voltage gives 6.5 volts, but Vin voltage is 6.2. So this will be stopped at this. So at this voltage it will be stable. And LED will be displayed. What value of LED will be displayed? It's 2 cube plus 2 square plus 2 power 0 plus 1. 2 cube into 1 plus 2 square into 1 plus 2 power 1 into 0 plus 2 power 0 into 1 is equals to 8 plus 4 plus 0 plus 1. That is equals to 13. So the answer 13 will be displayed here. Okay, this is very simple question which you can easily solve. So my question is, what will happen whenever 6.5 less than 6.2? Means whenever this VDAC is less than 6.2, it comes to the second case. Here VDAC 6.5, VIN is 6.2, right, in the last step. So comparator will be 0, so clock is not applied, and the output of AND is 0, output of AND will be 0, so this becomes stable state. So finally at stable state 13 will be displayed. So the answer is option D. This might look some complex, but if you revise once again, it will be very easy. Only 4 important steps here. The first step is you need to take this equation, just expand this. Expanding summation is not a big deal. Okay. Now in the second step, based on the given conditions, you need to derive. What is the thing is, whenever comparator is equal to 1, clock is applied and AND gate is enabled. So whenever comparator is 0, clock is not applied. So when these cases occur, whenever VDAC is less than VIN, comparator equal to 1. Whenever VDAC is greater than VIN, comparator equal to 0. So by using this and this relation, we should keep on solving by substituting or incrementing the binary values. So by the same time we should check the VDAC values. Okay, so we keep on checking the values at the point 1101. We are getting VDAC less than VIN is to be false. Whenever this is false, it is said to be stable state. Okay, I have written here, it is said to be stable state, where we can get LED display to be the decimal value of that binary number. The decimal value we calculated that to be 13. This was the second question. From the previous question we have seen that what is the steady state. Now this is the second question they have asked. The magnitude of the error between VDAC and VIN at the steady state is. At the steady state we have got VDAC as 6.5 volts. Okay. Now they are asking the magnitude of the error. Okay. The magnitude of the error we can get by error is equals to mod of VDAC minus VIN. Okay. Now VDAC is to be 6.5 volts minus VIN is 6.2. This is given in the question itself. So the answer will be 6.5 minus 6.2, that will be 0.3 volts. If you see here in the options, option B is the correct answer for this question. Okay.